Okay, let's try that again. So here we are. I'll give it a few seconds to get going. Hello, hello. Is it working? Let's see. Give it a few seconds to. All right. Okay. So let's continue. Having a rough day today. Having a rough day. Okay. So let's continue with the question. So what I was looking at before I felt the need to restart. Let's just phrase it that way. Is I was curious about the reverse iterator. Realized that you can use this base to get the base iterator from a reverse iterator, which is interesting. And the reason I was looking at that is there is a next permutation routine that you can use in C++. And I had often wondered about the permutation or implementation, excuse me. And yeah, I wondered about the implementation of the next permutation routine. And it uses some reverse iterators, and it also uses this base element or this base function. And let me see if I can kind of understand what's going on here. So let's see, you have some range of vectors, or you have, something, well, like ABC or ABA. Okay, fine. Or ABC is fine. It's something like ABC. You get the reverse and the reverse in the range, right? And then you have the left side from first to last, so from right to left is sorted until. That basically examines the range first last and finds the largest range beginning at first in which the elements are sorted in non-decreasing order. Non-decreasing order. So it's increasing right to left. Okay. Sequence is sorted with respect to a comparator comp. If for any iterator it pointing to the sequence in any non-negative integer n, such that it plus n is a valid iterator pointing to an element of the sequence, comp it plus n and it evaluates to false. I think basically the normal comparator is less than. That's what it means. So this less than. Here we could think about it instead of being in reverse, which is 0, 1, 2, 3. So I think this is actually a greater than. No. Yeah, this is like the less than basically, or less than. Be comp, be like the default, right? Because if the element to the right, which would be like, let's say 2 and 0, 2 less than 0 is false. Yeah. Okay, that makes sense. Elements are compared using. Oh yeah, there we go. That's exactly what this is. It says it right there. Yeah. And you can use comp instead. All right, fine. Fair enough. It's exactly as you'd expected. So going backwards, we're looking to basically say how much is this sorted in reverse. So if you had like ABC or ACB, for example, then B to C would be sorted in reverse. So then you would get going in the reverse direction. What iterator do you return? Examines first to last, so it doesn't include. What does it return? Forward iterator. What's the return value? The upper bound of the largest range beginning at first, in which the elements are sorted in ascending order, that is the last iterator it from which range first it is sorted, turns last for empty ranges and ranges of length 1. So an example is what is this? Oh, okay. So they have an example, 314159. Initial sorted elements, shuffle. Oh, sorted end. Okay. sorted size, initial sorted elements. Okay, 1 initially sorted elements. All right, so 4, and then why does this just keep sorting over and over, shuffling? Excuse me. Oh yeah, it just shuffles it a bunch of times and tells you. So it's 1 element, 3 elements. So the string sorted size. Oh, that's kind of cool. I like that. Times 2 minus 1. Oh, okay, it's kind of neat. The reason it's times 2 with a minus 1 is because there's spaces, so you gotta have an extra. I like that. That was clever how they did that. But the size. Okay, so where does sorted end point to is what I want to know. What the iterator points to. So here it would point to 1, I guess. Distance. So I'm trying to ascertain here. V begin to V end, first, last, that should be 3, right? Okay, yeah, so distance goes off the edge. So that means this is going off the, yes, so it goes off the edge is the returned iterator. Last iterator for which the range is sorted. Yeah, it's a little confusing. Upper bound of the largest range beginning at first in which the elements are sorted in ascending order. Yeah, so it doesn't, it's basically, what I'm trying to ascertain is whether or not the iterator that it points to is the iterator of the last element. Like if you were range from A to B, where B is included in your, I guess, elements, as opposed to like V begin to V dot end, it would be sort of like V dot end minus 1 would be sort of, yeah, it's hard to articulate what I'm trying to say here. And I'm also not very patient right now. But if you had a range A to B where B is not included, so which would be typical like V dot begin to V dot end, then does it, if it's sorted, do you get V dot end or do you get V dot end minus 1? That was sort of the question I was looking to ascertain. And you get V dot end is what they're expressing here. Yeah, so, okay, so we get some value. If left is not equal to r dot last, we'll come back to that. But let's say it is, right? The whole thing is sorted in from right to left, so it's actually basically backwards sorted. If it's sorted backwards, then we want to reverse, so we get that left dot base and reverse the whole thing. Okay, that's interesting. So the next permutation of CBA goes to ABC. Yeah, that makes sense. That's that would make sense because it goes to it just resets the whole cycle again, the whole sequence. But what they're doing, if you don't get right, so let's say you're sorted right to left for some section, and you're not going all the way across. Now there's a right side that you want to look at, which is going to be R first from right to left, then left, which is this is the sorted section. And now we're looking in the upper bound of the sorted section using binary search to find left. The value at left. Okay, well that's interesting. What? Isn't that just left every time? That's confusing. No. Oh, I see. Okay. The value at left So again, you've got your sorted range from right to left. The value at left is outside that range. Like if you dereference left, it's actually going to be the next value outside of the range. That's what, again, that was important for me to look at. Where is left with the is sorted until, what does that return? So if you had like 1, 2, 3, 4, 5 from right to left, and then a 6, then when you dereference left, you would actually get 6, not 5. Right, and so that's actually the element that's being used here. So they're looking for the first. So it's not just looking for. What's weird about this though is like, wouldn't this just give you, if you're going from right to left, and you're looking for the first value that's larger. So what can happen, I think, is that if it, so it's no. Oh, I see. So it's no. Oh, that's really interesting. Okay, so that value to the left can't actually be a 6 or higher, because then the sorted range would include that element. So the next element necessarily needs to be lower than, it needs to be somewhere in the range between R first and sort of left -1 dereferenced. Yes, that's what's going on there. Okay, that makes a lot of sense now. All right, so necessarily, because we didn't get all the way through it, there's some element like 1, 2, 3, 4, 5, and then 3 maybe, where that you can now binary search on that 3 through 1, 2, 3, 4, 5, and you can find where that bound would be. Okay, interesting. And then you're going to swap these iterators. I'm not sure what that does exactly. I'm assuming that would swap the values at those iterators. I'm not sure what that does. And then there's some reverse you do. So what is... Swaps the values of the elements the given iterators are pointing to. Oh, okay. Why not just do swap? The function template models the semantics of the swap operation given by swappable, that is, overloads of swap found by ADL and the fallback of standard swap are considered. Interesting. So, all right, that's fine. So no, it swaps those values. Doesn't swap the iterators, but swaps the values. So you had 1, 2, 3, 4, 5. So let's say you had 1, 2, 4, 5, 3. Right, 1, 2, 4, 5, 3. The upper bound would be the 4, and so now 3 and 4 get swapped, right? So now you have 4, 1, 2, 3, 5, 4, right? As opposed to 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. Now you have 1, 2, 3, 5, 4, right? After the swap. And why do that, and why does that matter? Because now you have this left and right, and then now this left.base is going to be reversed going to the last element. I'm not sure what that means exactly. The last element is on the right side, and the left part was actually the part that was sorted. So when I say left.base to last, now it takes that section that, so there's this section from right to left that's sorted. We say, okay, there's an element that follows that can fit somewhere in there. We swap it in, and then we take that whole section that's sorted and then reverse the whole thing. I don't know why that would be the next permutation. That doesn't make a lot of sense to me. So we had something like, what is that? 3, 5, 4, 2, 1. And then we would say, let's take 3, 5, 4, 2, 1. Let's take these elements, and we find 3. We say 3 fits where the 4 was. We're going to swap them, and then take this 5, 3, 2, 1 and reverse those. So now the next permutation of 3, 5, 4, 2, 1 is going to be lexicographical permutation is 4, 1, 2, 3, 5. Now, I don't know why that makes any sense, why that would be. So Interesting. Why is that the next permutation? Why does that make sense, is the question. You know, I don't know. Also, I don't think I need this to solve this particular question on LeetCode, but it's just while I'm thinking about this, I might as well go through it. So if I swapped any of the smaller elements from right to left, right? So I swapped 1 with 2, or 1 with 4, 1 with 5, or 2 with 4, or 2 with 5, right? That would actually be a smaller lexicographical permutation, right? I think that's the issue. Is you can't swap any of the elements in that sorted line, right? So you got to swap with something that's outside there, and in order to minimize, in order to minimize the overall size of right, to be the smallest sort of lexicographically larger element, which is the next one, you've got to do a search, and you got to say, okay, well, I can't swap anything, within those elements, so I've got to swap something to the left, and I should swap it with something to the right as well. But if I swap it with, like I had 3, 5, 4, 2, 1, if I swap 3 with a 1, then that actually puts me much smaller again, right? Because that 1 is smaller than the 3, so I can't swap with anything that's smaller. I have to swap only with something either 4 or 5, something that's larger. But again, I want it to be the smallest lexicographically larger sequence, so I'd have to pick exactly the upper bound, exactly the first element that's larger than 3, whereas all the other elements that are smaller than 3 won't do. And if I tried to swap with any elements to the left of 3, that would actually make those are more significant lexicographically, which means that I would end up going further ahead than I should. So you can prove that this particular swap will always give me something smaller than anything that I might swap to the left, right? And swap with to the left, and it's the smallest that I can swap of elements on the right side. So if I say, let's say, past 5, there's elements on the left side, we'll call them the alpha values, and elements on the right side, call them beta values. And I showed that you can't swap any of the beta values amongst themselves. If you swap any of the alpha values, we'll get back to that in a moment, but if you swap any of the beta values amongst themselves, you're going to get something that's actually lexicographically smaller. If you swap something then from alpha and beta, then you can show that the first alpha value that you could swap is as described. You would take the first element that's to the left of the beta values, and if you swap it with any of the other elements, again, it'll be any of the elements that are smaller than the actual value dereferenced of that alpha value, anything smaller than what that alpha value is, then it's going to be lexicographically smaller still. And then you can show that any of the other beta values beyond the upper bound that you might swap it with, that's going to be lexicographically larger. So you would pick the smallest of those such values, which is exactly the upper bound. And then on top of it, now if you consider any of the other alpha values to the left and swapping them with the beta values, you could show that since those are more significant, that you have a similar problem that occurs, but it's guaranteed that this number is going to be larger than the previous number. This sequence is going to be larger than the previous sequence that we found lexicographically. So we limit ourselves to only that one alpha value when combined with the beta values. Then you might consider, well, what if you only use alpha values and don't use any beta values? Well, you run into the same problem where for each alpha value, the lexicographically smallest possibility is going to be something to its right, which is either another alpha value or some beta value. And as mentioned, any of the alpha values that you use to the left, you're going to end up with something larger than the one that we just showed. So that's kind of a quick proof. It's not really great proof, but it works. This works. That's not a great proof, but it's convincing enough for me. Very interesting. Yeah, very interesting. And yeah, I'm not sure how exactly to make that more concise, but the basic idea is that yes, you need to swap two numbers. Oh, and excuse me, and there's one more issue here, right? So you have to take all of the elements that are left on the right side and reverse them, because now those should be sorted in reverse order. And now that you've updated your, really you could do is just take everything to the right and sort it in the reverse order is kind of the idea. So that's the lexicographically smallest. Forgive me, I forgot about that. That's actually the other thing. That's what the reversal is. So I guess it's not. I guess the what I just described is not really a proof because I missed that part. But basically, what you're going to do to get the next lexicographically larger element that's the smallest of such elements is you're going to try to find an element on the left side and swap it with something on the right side such that you can then sort everything on the right side. And it's got to be the next smallest element or the next larger element to the element on the left side. Yeah, and yeah, and you're looking for some element. So you have to have some element that's smaller from this increasing sequence from right to left. I don't know. Yeah, it's kind of interesting. Yeah. So basically, whatever next element is that's smaller on the left side, then what you end up with is once you swap, now everything to the right of that where that element was. So like I said, 3, 5, 4, 2, 1. Swap with the 4, you get 4, 5, 3, 2, 1. Now everything to the right of that 4, you want to sort that in increasing order, which it should be actually sorted in decreasing order. You want to just resort that, so that way it's the lexicographically smallest possibility of those permutations. I don't know. Okay, I don't know. It's not a very concise way of explaining it. Don't really fully understand it. I think I get it. It's pretty clever. Yeah, I mean, gotta think about this. Need to think about this. What is interesting at the very least here is that you can go through all the permutations in basically time proportional to the number of permutations. That's kind of nice. Another element of this is like, how do I know that that's the next one, right? How do I know that? How can I prove that? Excuse me. I guess you always have some sequence of elements. We'll just say alpha 0, alpha 1, alpha 2, ... to alpha n. Maybe 0, 1, 2, 3, 4, 5, 6, we'll say. We'll go that far. And then you've got some number from right to left of elements that are sorted in non-decreasing order. We'll call that, I don't know, this k of them. So I don't know, let's say 3, 4, 5, and 6 for k's. 1, 2, 3, 4. And then we're going to say, okay, there's this alpha 2. So this is sort of n minus k minus 1, something like that. Yeah, k is 4. It's actually just n minus k. Yeah, n minus k. Alpha sub n minus k. You're going to search for alpha sub 2 somewhere in that sequence to find the upper bound to swap the two. So we'll call that alpha sub j. So now we have alpha sub j. Swapped with alpha sub n minus k. And then that should still be sorted in decreasing in non-decreasing order, and then that whole thing gets swapped in the reverse direction. Okay. So why does this matter? Why? Yeah, all those k elements get swapped ultimately. Swapped and reverse. All those k elements get reversed, rather. You get a swap and then a reverse. I think the reasoning is that we just want to want to increment one of these elements from right to left, right? The least significant number, which is right to left, I want to increment that to something. And the only way to do that is to swap it with something else, right? And then after I've done that, everything to the right, I want that all to be sorted, smallest to largest. That's basically the idea. I think that's, if you could achieve that, that gives you the smallest lexicographically larger element. Yes. Okay, but how do you find a good candidate? Well, since you've got a swap with something, and it should be something to the right, because you want to swap with something that's less significant, something that's more, so you want to increase the more significant value. Obviously, if you went further to the left with something that's more significant to swap with, then you'd go further ahead than you should, right? You would go it wouldn't be the smallest lexicographically larger element. So it's sort of the minimal, the least significant element that you could find that can be swapped. So it has to be find something to the right of it that's larger. I think that's what it comes down to. Yes. So it's from right to left, the first element that has something to the right of it that's larger. Which, if you have an increasing sequence, none of the elements to the right are smaller. That's why. That's why it works this way. Looking for, from right to left, the first element that has something to the right that's smaller. Or excuse me, that's larger. Which basically boils down to looking through the length of the non-decreasing sequence until you find that element, or you don't find it at all. So you find that element, and then once you found it, then you could do a binary search to find the first element in your non-decreasing sequence, which is the sorted sequence that's larger. And then now you can swap those two elements, and then the elements that are to the right of the swap point, the element that you were interested in from right to left, sort all those elements on the right side. And since that's a non-decreasing sequence, it's still non-decreasing after you've swapped these elements. By how it's been constructed, the sorting is just a simple reverse routine. And then that's it. swap in reverse. And the added benefit to this, if this is sorted in non-decreasing order in reverse, then that means you're on the last permutation and you want to recycle, you just reverse everything. And so you have this if statement. It's just for that special case. That's pretty amazing. I have to say, that's pretty clever. That's like really not obvious at all. That's like not obvious at all. I didn't think of that. Could not have thought of that. Would have taken me a long time to think of that if I tried to think of that on my own, to realize that it works that way. Still kind of shaky on the proof though, but I'm fairly certain the proof is what I just described. You're looking, as I said, you're looking for the from right to left, the least significant element. So the furthest to the right element you could find that also has an element to its right that's larger. And so you can end up looking through looking through the monotonically increasing sequence, non-decreasing sequence from right to left to find that. And then you could also locate the appropriate elements using a binary search. And then once you swap those two, then sorting what you have to the right of that element, we'll call it X or I or whatever. Everything's from I plus 1 to the end. Sorting that is is the next thing to do, but and you can even simplify that sorting by just using a reverse, because those are basically non-decreasing, that sequence. That's pretty interesting. I don't know what to say. Okay, I think I got it. Sometimes you feels like you don't have it, you don't really understand it, but I think I got it. Anyway, all of that is to say, there is a way to get the next permutation. I don't know how to get the previous permutation. That's a good question. Going the other direction. I'm assuming the other direction would be from left to right, find the most significant. Maybe just do in the other direction. So to go backwards, previous permutation, right? So here we had 3, 5, 4, 2, 1. Next permutation was 1, 4, 1, 2, 3, 5. Previous permutation is probably yeah, that'll really test if I understand what I'm doing here. Previous permutation, I think, would be, we're looking for from left to right, because we're looking for the so from right to left, we were looking for the least significant element to swap. Now, if we want to go backwards, I think we still want the least significant element to swap, right? Well, okay, we can go backwards from 4, 1, 2, 3, 5. That might be easier. So actually, we would end up swapping 4 and 3, right? 4 and 3, and reversing 3, 5, 4, 2, 1, right? So now, how does that work? I think it's now we're looking, we could do right to left of the decreasing sequence, and then we find 4, and then we're looking for binary search for the, so right to left decreasing sequence, and then search for the element, the largest element that's less than 4, and swap them, and then do the same reverse. Huh. I mean, yeah, we just basically take the steps that we performed and go back and just go backwards. So 3, 5, 4, 2, 1 would be 1 only decreases once. So you get 3, 5, 4, 2. So 1 is just decreasing once. and the element to its left is 2. And now we're looking in that increasing sequence, which is just 1 for the, and we actually end up at the end, looking for the element just before that. But yeah, we're looking for an element that's larger than 2, so there's none, so it's just 2 and 1. And we pick that to swap, so you have 3, 5, 4, 1, 2. And then the elements that are to the right, which is just 2, those get reversed. So 3, 5, 4, 1, 2 should be the lexicographically previous permutation. And if I wanted to get its next permutation, so we have 3, 5, 4, 1, 2, 3, 5, 4, 2, 1, 4, 1, 2, 3, 5. So from 3, 5, 4, 1, 2, we said before we're going to go increasing sequence, which is just 2 to 1, find 1, search in the sequence for the element that is larger than 1, which is 2, immediately. Swap those two, 3, 5, 4, 2, 1, and then those values on the right side, which is just 1, reverse them, which is just the same position. So yeah, that works. We end up exactly where we wanted to be before. But why does it work that way? I mean, well, it works because we're reversing what we did before. I mean, that's true, but can I get there, like, in the first place? So in order to get the largest lexicographically smaller element, I would want to find the element to the right I'd want to find the largest element. No. I'd want to keep as many elements left to right the same between the two permutations. The most significant value should be the same. And then the swapping that should occur is I want to just take the as far to the right as I can. One of the smaller elements, swap it with an element that is smaller than it. Something like that. And then in order to maximize the size of this permutation, whatever is left over on the right side, sort that in descending order, right? So I find some element, it's going to swap itself with something to the right, and then whatever's left over on the right side, all of that gets sorted in descending order, which is almost exactly the same, almost exactly the reverse of what we described. But how do we figure out these elements? Which element's the best one to pick? Well, I need something that has an element to its right that's smaller. So it's going to be the decreasing sequence this time instead of increasing, from right to left, decreasing sequence. Find the first element that's not a part of a decreasing sequence. And then, so, with like 1, 2, 1, 2, 4, 5, right? We have 2 and 1. Or with 4, 1, 2, 3, 5, right? We have 4, 1, 2, 3, 4, 5. And then look for, in that decreasing sequence, in that element that we just picked, look for the largest element that is smaller than 4. Or the largest element that's smaller than 2. Now, why do you want the largest one? I actually think maybe it should be the smallest one, no? The reason you want the largest one is because I'm going to swap this significant value with that element, right? And that, and like I mentioned before, I want this to be lexicographically maximized, right? As large as possible. Smaller than what I have to what I started with, but still as large as possible. So that means I want the largest element that's smaller than the thing I'm going to swap it with. So in this case, 1, 2, 3, 4, 4, 1, 2, 3, 5. I would want to swap 3 with 4. And so I get 3, 1, 2, 4, 5, and then again I could reverse those 4, 2, 5, 4, 4, 2, 1, which is which is exactly the reverse of what we did before. So to go from 3, 5, 4, 2, 1, like I said, we're going to go non-decreasing sequence right to left, or excuse me, non-increasing sequence right to left, which stops at 2, from 1 to 2. And then a search on from 1 to the right, which is an increasing sequence, for the first element that's greater than or equal to 2, and then take an element to the left of that. So the first element that's smaller than 2. In this case, it's a 1. Swap those two, so we get 3, 5, 4, 1, 2, and then reverse everything that's to the right of that, the new position where the 1 is, which is just 2, which just ends up being 3, 5, 4, 1, 2 again. So we get 3, 5, 4, 1, 2, and then we could do the next permutation routine that we have over here, which gives me 3, 5, 4, 2, 1, and then finally the next permutation routine again will give me 3 and 4 get swapped and sorted. So we get 3, 4, 1, 2, 3, 5. I guess the next permutation here would be 3, 5, 4, 1, 2, 5, 3. And then to go the other direction, it would be 3, 1, 2, 5, 3, which gets swapped to bring me back to 4, 1, 2, 3, 5. Yeah, that's 4, 1, 2, 5, 3. Yeah, it's pretty interesting. It's pretty interesting. I could go think about that for a while. Not necessarily related to this question, but it kind of is because we're looking for previous permutations, right? So, given an array of positive integers array, not necessarily distinct, return the lexicographically largest permutation that is smaller than array that can be made with exactly one swap. Excuse me, if it cannot be done, then return the same array. Note that a swap exchanges the positions of two numbers array of I and array of j. So this doesn't have the reverse. If I did the reverse, then it would just be the exactly previous permutation. But with one swap, we don't do the reverse, I think. Yeah. If it cannot be done, return the same array. Swap exchanges the positions of two numbers. So yeah, this is basically, yes, we could glean from this information from the that previous permutation algorithm that we just read. We can figure out a relatively straightforward way of doing this. So basically it's the same thing, except we're just not going to do the reversal. So it's going to be like the following. So we had auto R last and auto R first, and that's like standard reverse iterator. I'm kind of wondering, how did we do this? How did they do this? Make reverse iterator. Ah, okay, I like that. Make reverse iterator, that's better. Of array.begin. Array.end. Just for the sake of oh, I think someone was explaining you shouldn't Someone was explaining that you shouldn't use the end line because it flushes the buffer, which is not necessary in a loop. So typically you could just use a new line character, which I didn't really think about that. I hadn't thought about that until someone showed me that. Someone pointed that out. So output 3 2 1 1 2 3 3 2 1. Oh no, standard out 1 2 3. Yeah. Okay. So it's it works. 1 9 4 6 7 7 6 4 9 1. Okay. I mean that does what I think it's gonna do. So that's cool. Great. So now again, what I'm gonna look for is sorted. What is that? There was something or other. CPF sorted until. Is sorted until. Yeah. So in reverse, I'm looking for I want to go backwards, right? So I'm not looking for it being sorted in non-decreasing order. I'm looking for it sorted in non-increasing order, which is going to be the left side is sorted until, and I'm going to use the comparator as a greater symbol, greater comparator rather than a lesser comparator. And this is going to be R first to R last, right? And now the idea is if left is equal to reverse last, or if we go all the way through, then we could perform the swap. Otherwise, we just return the array as it is. And the swap is, I've got to return, I want to run a right side, right? The right side is going to be upper bound. So I think I said before, it's actually going to be a little bit different. It's going to be a lower bound decremented. Lower bound of the left side. Or alternatively, you could do, well, this is a reverse iterator, right? So this is going to be sorted in the other direction now. Yeah. You could do. This gets confusing, right? Ready for this? Use a different comparator now. Now I don't know if it's upper bound or lower bound though. I think it's probably still upper bound. But if we're going R first, R last, and really to left, yeah. So that gets real confusing, huh? And then there's an iter swap of left and right, and that's actually it. But this part might be wrong. This could be wrong. I have to kind of revise that. But yeah, just don't do the reversing part at the end, I think. That's it. Oh yeah, done. Got it. Ta-da. That's it. You gotta be kidding me, really? It's that simple? Of course. Of course. Yeah. Let's see, let me do another that. So let's try to do this. For I in sequence of 1 to 8. Whoa. Do echo hello. Done. Okay. And now I want an awk script to run. And this is going to be awk of, let's do begin. I think if I just do it this way, right? Let's just do print hello. No, all right. Okay. Oh. Okay. Maybe I don't want to do it that way. I think I probably don't want to do it that way. Okay. All right, I want the following. srand, print rand. So I tend to get this confused. This is going to be date plus s. Okay. I'm always confused about this. So do I need another? Okay. So for some reason, this doesn't work the way I'd like it to. Invalid character expression. No. I don't know. I don't know. It doesn't. I could do this. I think this works. Nope. Oh. I don't know. I don't know. Why is this such a problem? Yeah, I always get confused when I try this. I feel like I should know it by now, but I tend to just not really understand. Just kind of doesn't do what I want it to do. Date %s %n. Just want the date in nanoseconds. Ooh. Okay. Syntax error. Can I not just run this? Invalid character expression. How about this one? Oops. Doesn't work. No. It's not what I want. I don't know. I don't know what to say. Yeah, I mean, Okay. What is going on here? Syntax error. I had something like this before, it just didn't, it's not working. I don't know. What did I do? I want this to be another command. That's kind of what I'm trying to do. Run this command. Can I not just... So this is fine, right? This is fine. Then... Oh. Echo, echo. I'm confused. I don't know, I did something before that every time I try it again, I don't understand it. Shell scripts could be not so obvious what's going on with command substitution and whatnot. I just want a random number based off the nanoseconds of the clock. That's what I'm trying to do. Just put that into my awk script. So if I run an awk script, and it says srand something, and then print rand, right? Okay. And then I say date plus s, percent s, percent n. Is it syntax error? Syntax error. That's bizarre. This is bizarre. Maybe gives me some kind of syntax error. I don't really know. Maybe that's it. That's not right. I need a new seed value each time. That's confusing. Maybe this is the issue. It's not giving me syntax errors this time, but this is definitely not right. What? What is going on? Oh, this is so confusing. Okay. I don't know. I don't know what I missed. I'm missing something important. Not in Bash. How do I get the current? This is what I want. %s, %n. But how do you? Oh my goodness. Oh. Very frustrating. Look at this. Yeah. All right. Date get line rseed. Oh, okay. No kidding. Hold on. Awk. Begin. srand. Date plus %s. %n. Print rand. Okay. So it's not doing what I'm expecting, right? Just simply not doing it. Get line. Maybe this has to be converted to an integer. Oh, what is this get line? Okay. I don't know why I need that. Didn't need that before. What? What is this? Why? What is this get line? Oh. Used in several different ways, should not be used by beginners. One finds a record, 0 into a variable. What is this? Read the next record from aux input into the variable var. Oh, okay. No other processing is done. Suppose the next line is a comment or a special string. I want to read it without triggering any rules. Oh man. Okay. Wow. So you can read into a variable from a pipe. Okay. Hmm. I mean, that's pretty much what I wanted. I don't know. I don't know. Okay, fine. We'll do it that way. That's easier. It's easier to think about what's going on there. It's confusing otherwise. Anyway, all I wanted to do was get sequence of test cases. That's all. So it could be between 1 and 10,000, 1 and 10,000 are my numbers. Okay. All right, fair enough. So get my seed, and we're gonna print. So X is gonna be the test case. We're gonna do it 8 times. We're gonna say 4. Print X. Int I is 0. I is less than 10,000. Increment I. X equals X, comma. Could be yeah. Let's do rand 10,000. 1 in 10,000, I think it was, yeah. As an integer, comma X. Then at the end of that, print X. I'm gonna say awk or echo. Add these. Print these. What do they call that? Add these. A few things to say. I also want to run a set command here. Just take the last character and remove it. Something like this. Okay. What did they say? Oh, what? Oh, what? What? Syntax error somewhere. Oh, it's the set commands. All right, let's remove the echo part. Most of the echo part. What am I doing here? Let's remove the set part too. Just remove that altogether. This is the awk script. Doesn't work. Not working properly. I just don't. Okay, so that's an issue. All right. I think I need this here. It's wrong. Oh, this is so irritating. It's like, why? What the hell? Excuse my language, but what's going on? Why is this happening? 4. I see. Oh, so I'm used to. Okay, I see the issue. Bad. That was bad. Okay, there we go. That's more what I wanted. All right, there we go. Okay. Okay. Gulp. Sometimes make mistakes. Sometimes I make mistakes. I don't realize what I'm doing. It's true. Okay. You know, 10,000 is kind of a lot, quite frankly. Let's go like 100. 100 might be better. 1,000 maybe? Let's not do 1,000. Let's do like 100. You know, I don't know. I have to say I've been taking a lot of time to write the same script every time, just to do some fuzzing, and I'm kind of annoyed. I don't know why it's taking me so long to do that. It's just it should take me it should be pretty quick. It should be a relatively quick thing where I just kind of whip up a script quickly, and I can do my fuzzing after that, and I'm on my way. Just write a quick script, do my fuzzing, make sure I'm not totally wrong, and then yeah, let's do like 3 of them. But for some reason, I struggle with it. I don't know what it is. It's not obvious to me as to why. Just seem to I'm gonna go for not yet. Oh. A couple more things I need to check. 1, 1, 2, 2, 1, and 10,000. Yeah, I don't know what to say. I have this habit, I guess, of I don't even know what to. Oh no! Sometimes I just get it wrong too. I don't remember what I was gonna say. I was gonna say that I can't believe this is wrong. Of course it is. And the fuzzing didn't get it. I should have. I forgot to do some like tighter cases. That's what I should have done. If I did like a tighter case like this, I would have caught it, I think. Of course. 3113. Yeah, okay, I would have caught it. I forgot to do that. I forgot. No. Alright. Bad. Of course. Just forgot. Oh, I'm having a rough day today. Hour and 15 minutes? Okay, not great, but yeah, I know how to write this script. I know it from heart. I just forget. I guess I just should do the get line seed to seed it every time, and then I should be fine. I forget things like, you know, this shouldn't have an int in front because it's an awk script, not a C++ or loop. Yeah, I don't know what to say. Sometimes I make mistakes, but anyway, so yeah, I should be able to write that script a lot faster than I did this time. And also, this was pretty bad that I got this wrong. Excuse me. So yeah, this is incorrect. This is the part that's wrong. I thought this might be wrong. This is wrong. This is wrong. So what ends up happening is it goes right to left. Is it sorted in decreasing order? which it is up to this 3, right? And then I said, okay. I say, okay, I've got to take this 3 and swap it with something, right? And I swapped it with this one when I should have swapped it with this one. Yeah, I think this is a lower bound. Upper bound, lower bound, is it? Because this is confusing because it's an upper bound, but it's using a greater than, which means upper bound normally you're looking for something that's, and it's going the reverse direction, so it's even more confusing. Upper bound, you're normally looking for something that's greater than, strictly greater than your target. And if I swap with a greater than symbol, and that's using a less than symbol, greater than symbol is now looking for something that's strictly less than. But it's going to find the first thing that's less than my target, which is 3. So the first thing that's less than 3 is going to be 1. It really should be the last thing that's less than 3. Yeah. Not the last thing that's less than 3, but the one that's furthest to the left, that's less than 3, not the one that's furthest to the right. I see. Well, that's awkward. Oh, I see. Could just do lower bound of base. Yeah, that might be better. Yeah, it's confusing. Oh boy. Okay. Well, let's try that then. Let's go the other way. Left base, right base. So here, left base, I think, moves to the right. Right base, right first, moves to the right here. We search from here to there. We say, we find first element that's still this one. This doesn't work the way I'd like it to, does it? No, it doesn't. No, it doesn't. Oh, that's awkward. Oh, I don't know. I don't know. Yeah, if I search right to left for something that's smaller than 3, largest permutation that is smaller than array that can be made with exactly 1 swap. Oh, this is awkward. Well, this is awkward. Gee. Gotta be kidding me, huh? I mean, what am I supposed to do with this? If I swap this 3 and this 1, I get 1, 1, 3, but then these get swapped to 1, 3, 3, 1. Right? That's what it's supposed to be, 1, 3, 3, 1. But I can only do one swap. Ah, it's bad. I got it wrong. Oh, it's not good. Not good. Not good at all. Gee. Not great. Not ideal. A struggle. What do I do here? I gotta think about it, I guess. Three one one three 1 1 3 3 3 1 3 1 3. I mean, can I just swap with something that's smaller? What is going on here? Oh, I see. Is that the right idea here? I don't know. Because you can only perform one swap, right? Swapping with anything to the right would make this larger. Swapping with this would make it smaller, but not the largest. And swapping with this is larger, yeah. And normally, to make this the largest lexicographically, like to make the previous permutation, these would all get swapped. Or not swapped, but reversed. But it's, if I put an extra 2 in there, run into some trouble, huh? Oh, man, disappointed. Could have tested for this. I'm also kind of annoyed because I don't really know. I mean, I could do a linear search too. I mean, that's not like It's not like I have to do it. It's just a little weird because it feels like I should be able to do this efficiently. So actually, I wrote this correctly the first time around. I did this right. It's just supposed to be first one, not the second one. So this actually goes from right to left and looks the first time that I find something that's less than 3, just 2. Which is a little weird because, I mean, I could just do the following. I could just do this too. Well, right is not equal to left, and let's just say right plus 1 is equal to right. Could also do this. It's like, okay. This also works. Or does it? Oh. Maybe that's what I need to do. I mean, I think that's fine. Just keep it simple. Afraid to. Oh boy. Afraid to submit it now. Oh no. There's kind of a small caveat there that I missed. Darn. 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 That kind of sucks. Oh. Okay. Do it a few times. We'll just do maybe 3 times. Oh, not that one. All right. And one more. All right. This could still be wrong. That would suck. Hey, you got there. Okay. Okay. I don't know what to say, man. You know, whatever. Okay. I'm having a kind of a hard day today. Hard day today, hour and a half, not great, not ideal. Oof, long runtime too, ouch. Let's try to go submit it about 6 more times. 7 submissions. Ah, it's so slow, jeez. It's really slow. 1, 2, 3. I bet you could do this with one pass. I think that's why it's so slow. 1, 2, 3, 4. So 2 more. Okay, that one's not bad. 1, 2, 3, 4, 5. Okay, that's good to get 90%. All right, that's not bad. Not the fastest solution, but it's reasonable. It's reasonable. I'll submit one more and then we'll go on to the next one. Yeah, I mean, it just kind of messed that up, you know. That's the linear time you could do it in, and it just kind of goofed it up. I don't know what to say. Yeah, could have thought about it a little bit more, I think. All right, so I think I'm gonna stop there. Thank you for watching. If you liked the video, give it a like, and like the stream. Follow me on YouTube. And yeah, I'll stop here. I might want to take a break. Like I said, I'm kind of feeling a bit down today. Take a break and then maybe come back and do some more problems. But the idea is to restart the stream on another problem. So yeah, take care. Talk to you soon.